So, it's 9, so I'll just start. There might be a couple of latecomers still coming in, but we'll just start. So, it's getting more and more advanced, as you might have noticed. We might start delving into some things which you might not have seen during your undergraduate. So, we're week 9, but lecture 8. And last week, I told you all about exploratory factor analysis, which some of you might still have done, but it's unlikely you will have done today's component, which is confirmatory factor analysis. And so this is part of structural equation modeling. And the goal is not to make you a structural equation modeling expert, because we could easily fill 12 weeks or a full year-long module on nothing but structural equation models. That would actually take an entire separate course, but you should be able to apply the basics and understand when you come across. So you should be able, once you see a structural equation model, sort of understand sort of what it means. So that's the goal. If you're actually going to go out and apply this in the field, then I recommend you read some books and you spend some time delving more into it, because again, I'm just giving you the highlights, and you're going to have to delve a little bit deeper if you, for example, if your supervisor wants you to do confirmatory factor analysis. So we're already on assignment 2, like for a couple of weeks now. And so after today, you're able to do a section on confirmatory factor analysis via structural equation models. And just a reminder, I've noticed that I know you're all busy and focusing on the assignment 1, and also focus on Chris's bit, and probably also doing things for your internship and posters. But I noticed that that there's less and less people submitting exercises as we go along for the week. So don't leave it too late. And it's still beneficial after every lecture to go and do the exercise, because it will be good preparation, you'll get some feedback, and it will keep you going. So I know you're probably also honing on your R skills for doing the actual assignments, but I would recommend you keep up with the exercise, because otherwise you're going to have a big chunk at the end to still get through. Yeah. So it might be different from your undergraduate, because it's really stepping up, and you have to be working on multiple plates spinning at once, and still trying to complete everything. So last week we covered exploratory factor analysis, and you remember that factor analysis is used to find a set of unobserved variables or latent variables or dimensions. We had the example of personality, so we don't measure personality direct, we use a questionnaire, and that sort of reveals the big 5 or the big 6 or the big 2, depending on which school you're in. And the idea is that they account for covariance among a larger set of observed variants, so that using these items, we can, for example, measure introversion, extroversion by using a set of those items. So basically, usually it's done in questionnaire validation. So you have a large number of questions and you want to reduce that complexity. So you have 60 or 120 or 200 questionnaires about questions about happiness or personality, and you want to tap into the dimensions below that. So again, think back to the personality example from last week. And so hopefully it should also be clear why this is relevant to you, because as psychologists, usually you might be brought in order to measure something, in order to develop a questionnaire. And several staff, for example, have developed new questionnaires on, for example, cybersecurity, on digital hoarding, all sorts of other things which we might not have measured before. We might develop a questionnaire to go out and measure people's attitudes or people's perceptions or people's emotions towards certain behaviors. So why is this useful? As I just said, most of this questionnaire validation. It answers these questions about, like, how many dimensions do you have in a more rigorous way. So do we have 5 or 6 dimensions of personality? It's something we can answer in a more rigorous way when we do confirmatory factor analysis. Usually also when you have a measure, you want to find out whether it measures the same thing across different populations. So suppose you have a measure on stigma, and you want to apply that to many different medical conditions. You want to make sure it's measuring the same for people, for example, with a skin condition versus people who have HIV/AIDS, for example. So you want to make sure that the measure you're using is consistently measuring the same thing across a variety of groups. So that's also something which structural equation modeling can answer, and which confirmatory factor analysis can answer. So are we measuring the same thing across different units? Another example would, for example, be taking an intelligence test. You could take that to a school with low socioeconomic status or a school with high socioeconomic status. Can we be certain that these intelligence tests are measuring the same thing when we go to different environments? Yeah. Often also a purpose of this is we start out with a large bunch of questions. We might have a pool of 250 candidate questions. That's way too much for our participants to do. So can we drop some questions which are not discriminating between different variables, between different latent variables? So there might be some questions which are less good at, for example, discriminating between extroversion and introversion than other questions. And so then we can drop those. So that's also the purpose. And ultimately, so again, thinking back to the examples of schools, you might then use those intelligence scores to correlate with something else. For example, with reading test scores, or with physical activity, or with mental health. So ultimately, the purpose might be that you use those questionnaires to then generate scores on those latent variables, and you use those in further on analyses. Yeah. Any questions so far? Hopefully, I've convinced you why this is useful, and I'm telling you a little bit about questionnaire formulation. So, exploratory factor analysis, as we saw from last year, has lots of potential for ambiguous decisions. Yeah. So we had to sort of look at a plot. I gave you 6 or 8 different ways in which people have done exploratory factor analysis. So some people use the Kaiser criterion, some people look at the plot, some people use very simple structure tests. So there's a bunch of researcher degrees of freedom. There are a bunch of ways in which you could decide, for example, how many factors you would extract. And also there's different guidelines, for example, on how you remove good or bad items. And that is quite ambiguous in some cases, yeah? So you might give the same data set to 2 researchers, and they might come with very different conclusions in terms of how many factors there should be or how many items load on each factor. So with conformity factor analysis, we force you to make more explicit decision, and there are actually explicit tests to say this one is definitely better than this other one, yeah? To the degree that we're able to do that, because there might still be some cases where the data don't allow for discrimination. So some of the terms are terms we've seen last week. So again, we have an observed variable, sometimes known as an indicator or a manifest variable. It's something you've measured. So an item from a questionnaire, that's an observed variable or a manifest variable. So if you were doing a happiness questionnaire, it would be a question on a happiness questionnaire. And when we draw these type of things, then usually they're denoted with rectangles. So you might also remember from last week, we had rectangles and circles when we were plotting our factors. Then we have the latent variable. So this is the unobserved or the construct or the personality dimension or whatever dimension you want to call it. We assume that these are the underlying variables causing people to respond in a certain way. They're answering that they like being part of going to parties because they score high on extroversion. Yeah. So these are the things causing, so to speak. So that's also why people tend to use causal modeling as a term. They tend to cause people's responses on certain items. And so they're the things we haven't observed, like, for example, intelligence, openness, well-being. So they're the labels which we attach to these causal dimensions. And they're denoted with a circle, again, similar to what we had last week. So we also have in our diagrams covariances, so things which are correlated. So those would be double-headed arrows. You can think of them as correlations, but they're not standardized. And residuals. You remember residuals from regression. We also looked at residuals. They're basically the trash bag. And usually we don't want to see any patterns in the trash bag. So if our regression, for example, is perfect, we expect that the residuals are normally distributed, right? So that's some of the things that we looked at before. And so if there are meaningless, hopefully it's all meaningless, but there could be that we've done our model and we find still some things are correlated, so it means we haven't made a perfect model, and we can then go back to our model and examine if we can improve it by, for example, correlating certain things. So if there are correlations which exist in our trash bag, perhaps we can go back in our model and see if we can model those correlations to see if we can get a better fit to the actual data. Yeah, and so they're usually also pointed with double-headed arrows between observed variables. Yeah, any questions so far? How's it done? This is the part where I refer you to maths. You can look it up yourself. It's matrix algebra, so basically we can cast every single thing, also like from factor analysis last week, as a series of equations which are set in a matrix. We can solve that matrix. We can try to find out if there's one solution or more than one solution. Last week, for example, with factor analysis, we then rotated that matrix to get interpretable coefficients. So behind it is matrix algebra. I'm not going to teach you all the matrix algebra, but basically we can recast all the equations which we draw on a diagram into a matrix, and then we can solve that matrix or attempt to solve that matrix. And that's what structural equation modeling does. And we basically use some very, behind the scenes, we use some very clever algorithms like maximum likelihood or some other things to estimate all the parameters in that matrix. So, but you're going to have to read more about structural equation modeling in books in order to understand matrix algebra. Again, my purpose is not to teach you maths or matrix algebra. My purpose is to give you an understanding in how you, what you have to do as a psychologist and how you can interpret some of these results. So outside of R, you might have a supervisor who doesn't use R, but they will have used something specifically for structural equation models. There's M+, Lizarel, Leighton Gould, Amos. And so this is also a part where I'm trying to convince you that why are we no longer using SPSS? Because this simply doesn't exist in SPSS. If you wanted to do this, you would have to use a different package anyway. And the closest one related to SPSS would be Amos. But just to give you an estimate, I think as a private person, it costs you around $1,500 for a license a year, if I'm not mistaken, or up until the next upgrade. So it comes at a cost. And the benefit for R is that it's open source, it's free, so we can do these type of things for free. So again, as we've had with when we were doing linear models, and we were doing all these other things, there's many different ways to do structural equation models in R, because ultimately it's matrix algebra. And one of the things, some of the things have been developed more by geneticists, like OpenMX, but we'll be focusing on lavaan, which has been developed by psychologists, and today also we'll focus mostly on lavaan. But you might come across some other packages which can do the same type of thing. But lavaan has a very intuitive syntax, and it's continuously actively developed, and it's been developed by psychologists, so that's why we're interested in this. So I'm going to give you an example, and this is a subset from the Holzinger-Schweinfurt data from 1939. It's looking at intelligence as captured by three performance things like visual performance, textual performance, and speed performance in a bunch of children in 2 different schools. In the original paper, there's more schools, but this is a subset which we'll be using for our purposes. Yeah. So this is something which we have as a model. So there's 3 items loading on visual, 3 items loading on textual, and 3 items loading on speed. And we've modeled the covariances or the correlations between these other things as well. So we assume if kids are very good at speed tests, they're also going to be very good at visual cognition. Yeah. Any questions so far? So notations. This is perhaps not the fun part. So we use F, for example, to denote factors. So you could have something like composed of factors and still observe variables. So these are just old notations. Just bear with me for now, like how you write things. You sort of know by now that the tilde is sort of the thing which says determine something else, because that's also what you have with regression, right? So that's why we use a tilde. And so this, for example, would be a superfactor, like a factor which is made up out of 2 other factors, like factor 2 and factor 3. Yeah. So these are all just notations. We can define factors as follows by the observed. So if a factor is only composed of these observed variables, then we use is and the tilde to say this type of thing. So this would correspond one with 3 observed variables, one with 3 observed variables, and one with 4 observed variables. Yeah. So again, this is all just showing you notation. We could have variance. We could model the variance for an observed variable, and we could do that by using double tilde. So that's variance. This is covariance because this is between y1 and y2. Yeah. And so we could also have covariance between factors. So again, this is just the degree to which things correlate or covary. Yeah. So intercepts. So if we have fixed intercepts, it's just the tilde 1 as you had in regression. If we have them related to observed variables or factors, we again use tilde 1. This might be necessary sometimes in order to constrain things in order to be able to estimate it. But don't worry too much about them for now. Okay, so if we go back to our example, this is what actually would look like, because the nice thing is we don't have to specify the correlations between these covariances, because lavaan will automatically assume they're covariant. Yeah. So if you only wanted to make sure that you only had this, for example, then you would have to explicitly write all the relationships. Otherwise, it will by default say all these latent variables are associated with one another. Yeah. So visual is made of x1, x2, x3, textual x4, x5, x6, speed x7, x8, x9. And that's what the notation would be like of this factor model. So these are also known as visual models. So usually you would first draw your model, And Alex has done some of these things, just drawing lots of models and then actually plotting them. So if you're working with loneliness questionnaires, for example, you would draw out a factor structure which you would expect, find out which items go underneath it, and then model that. Yeah. So if we do this in lavaan, we place them in single quotes. So now we take this, which describes this factor model, and now we call something, and this will be a list because it's just a bunch of text, and we use single quotes, so not double quotes, to define this. And as with other code, we can use hashtag to annotate the model if you want to. Yeah, so this will not be read, but this will tell us it's a three-factor model. Yeah. Okay. So before we move on and actually do our factor analysis, the same assumptions apply to what we had last week, by and large, for factor analysis. So basically, we're dealing with regressions. So and for factor analysis are a variant of that. And so if there are no meaningful correlations, remember from last time with this KMO test, and things had to be marvelous, or we want everything to be like a very good loading. And so in this case, we have everything above 0.7. No, this is 0.59, 0.68, but the average is 0.75. So it's okay, but there's some items which don't correlate well with other items. Yeah. So as before, we do this type of check. So what I do here is I call the lavaan data, call that the F data for factor analysis or whatever you want to call it. I use a subset, which is columns 7 to 15, because that has the variables which we're interested in. And then we do the KMO on this, because this only needs the things which we're going to factor analyze in it. Yeah. So a data set might have it. So you could also solve it via mutate and dplyr. In some other cases, we will have done that, or via select and subset. So, but this is how I've managed to make a small reduced set and then do the KMO test on this. Yeah. So you remember also that we were checking if things were multivariate normal. In this case, it's not multivariate normal. You can see by bringing up this plot. But remember last time for some of the other data which we had like serious disturbances and way more off the line. Yeah. So it's not great. So one solution is robust estimation. So if things are not multivariate normal, we can change the way we solve these equations to make sure that it's done in a robust way. So it's not the same as in regression, because regression is sort of a one-shot thing. It's ordinary squares regression. So we're already improving because we use maximum likelihood to estimate these type of things. But still, you might want to check how these results are upheld. For example, if you bootstrap or you do some other things to make sure how robust it is. Yeah, because this tells us it's not multivariate normal. And if you want to look at the actual tests, it's not multivariate normal on skewness and kurtosis, and you have very small. Well, this is 0.05, and you should know that these are quite powerful tests. But this is highly significant, so you definitely have quite a lot of skew in your data. Yeah, probably all the kids do very well, or they don't do very well, and that's why you have some skew in your data. Okay. So now, actually, we can go out and do the actual confirmatory factor analysis. Again, I've loaded here for most of the time. I've said again, require lavaan. If you've done it once, there's no need to do it every single chunk. But just to remind ourselves, we call an object which is fit. CFA is to determine that we're doing confirmatory factor analysis. We can also do SEM, and then it's a more generic workhorse to do all sorts of structural equation models. This will know that it's a confirmatory factor analysis model. This is the model that we specified before. If we go back 2 or 3 slides, that's that model, yeah, which we have stored as an object. So lavaan will now read that in. We tell it which data to use, and that's all we need to do for a basic factor analysis. Yeah, I make a sink because it's lots of output, and it will all go into that sink. Yeah, let's have a look at what's in that output. So if we go to you'll notice that there's not a perfect correspondence because I've updated the lavaan package. So this is 0.5 rather than 0.6, but it doesn't matter. It's just it's just different versions of the same thing. So this is something I ran previously. So you get lots of output again. Yeah. So some of the things should ring bells because the TLI, for example, is something which we saw with factor analysis last time. Also, the RMSEA is something which we saw before, like when we were doing factor analysis last time. And what we then have further down, so this is just some things about how it was estimated. You could compare different models. I'll come to this when we compare models. And there's some fit statistics here, like the CFI and the RMCA. This is also a fit statistic, but it's not as common. And then the thing you might care about more is all the things that went into our model. Yeah. So you remember that we had visual, textual, speech, like all those variables. You can see that one is already always 1, and that's because it's easier mathematically. So if we just constrain 1 and put 1 to 1, we can rescore all the other variables to that. Similar as in regression when you do dummy coding. So if you have, let's say, 5 categories, then you only need 4 categories and a reference category in order to represent those in your model. So similar to this, it's just always picking the first one and constraining it, which means it doesn't have a significance test because everything is compared sort of to that other test when you're solving this way. The good thing is they're all highly significant, they're all loading in this way. Now these are unstandardized coefficients because I didn't ask for standardized coefficients. So, but you can tell already that all these loadings are significant. Yeah, so all those arrows going to those latent constructs are significant. These are the correlations or the covariances between, I should probably always call it covariances because covariances and correlations aren't exactly the same, even though they are closely related. So this is visual relating to textual and to speech. You can see also that they're related. And these are the estimated variances, like how much variation there is on all those on those trash things as well as on the latent variables. Yeah. So lots of output, but these are usually the things you want to look for first to see sort of if your items are loading on what you said they would be loading. Yeah. If they don't, then you might have to go back and remove some items, for example. Any questions so far? So a big chunk of output, but similar to what you had from factor analysis last week, we're looking at evaluating the loadings onto these factors. Okay. So, some familiar faces. So you remember that we saw the TLI. It was an acceptable fit, also based on a CFI. But if you go back, this RMCA value wasn't good. It was not like, you remember the magical cutoff point was 0.05 or something for RMCA. And so that even if we take a 90% confidence interval, it doesn't cross into 0.05. So it's a poor fit on RMCA, but what you should know perhaps is that this RMCA measure is very sensitive to sample size. So larger samples, better RMCAs. So if you have quite tiny samples, then you should perhaps weight it less because you will be less likely in order to get that close to that threshold. Yeah. So the CFI is another fit of a measure, and many measures exist, but most commonly people report this RMCA, the CFI, and the TLI. Yeah. You also have what did I say? The SMR. Where did it go again? The root mean standardized residual, or what? Root mean square. Too many measures. Yes, that's the one. So lots of things in here. So this one, the standardized root mean square residual. That sometimes also gets reported. Depending on your supervisor and depending which journal you go to, people will want different things, but most commonly people report the RMCA, the CFI, and the TLI. Yeah, and sometimes also the chi-square, which you had at the top. Yeah. So it will depend which journal, so you'll have to check. But yeah, so that's what is typically reported. So now we're going to try something hands-on. So I would like you to return to last week's model we tested in class. So you remember that we were doing these things with teachers. So if I click this, then hopefully it will give you the M255 datasets which you used. Hopefully you've saved that somewhere. We'll use the subset of that dataset to do the factor analysis on. If not, you're going to have to start from scratch. And I would like you to make a 3-factor model in advanced format and evaluate fit measures. So make 3 factors. You remember that last week we extracted we first extract lots of factors and then could come up with a 2 or 3 factor solution. So look at those items and then try to load those. Okay? It will depend if you sort of remember from last week and if you were here last week. But yeah.